So in the first video on kinetics, we took a look at rates of reactions, how to express them, how to compare the rate of one component in the reaction to another. What we're going to do here is take a look at rate a little more closely and how concentration will affect the rate. And in order to do that, we are going to look at something called a rate law. And so a rate law is simply an equation that shows how the rate of a reaction is dependent upon the concentration of the reactants. Notice that the rate is only dependent on reactants, not products. So this is something a little bit different than equilibrium. Equilibrium was products divided by reactants to get the equilibrium constant and so forth. Rate law, all we're looking at is the reactants because we don't care about the products. How fast the reaction is going to go is based solely on the reactants. So you got to keep that in mind. So, but we're going back to our generic equation that we've used many, many times. The rate law can be expressed in the following manner. You've got a constant, a rate constant. This rate constant is going to change with temperature. You increase the temperature, you're going to increase how fast things collide, and so forth. So this K is only good for one particular temperature. You've got the concentrations of all the reactants multiplied by each other, but this is something that's very different. They are raised to some number, not necessarily the number of their coefficient. So note this is m and n. This is not little a and little b. So these m and n are whole numbers that are referred to as reaction orders. Again, they are not coefficients. They are reaction orders. So that's what we're going to take a look at next. How do we figure out these reaction orders? So you can have, typically, you're going to have one of three reaction orders. You can have either a zero order, a first order, or a second order. So in a zero order component, the reaction is not influenced by that substance at all. So basically what we're saying is it doesn't matter how much of that reactant you have, you cannot make the reaction go faster or slower. That's a zero order. To show that, you simply say the rate is equal to the constant times the reactant to the zero order. So it essentially, anything raised to the zero is going to fall out of the rate equation because it winds up being a value of 1. Okay, first order is where you have a direct relationship between concentration and rate. So if the concentration doubles, the rate doubles. And so we show that by writing it this way, raised to the first power. And then a second order is a square relationship. So is the concentration doubles, the rate increases by a factor of 4. If the concentration triples, the rate increases by a factor of 9, and so forth. And so you see the rate expression shown like this. So the numbers are typically either going to be m and n are typically going to be either 0, 1, or 2. For us this year, they definitely are going to be 0, 1, and 2. All right, so let's talk about an overall reaction. So each individual component has a rate order. You have to determine their rate orders experimentally. The overall reaction order is going to be the sum of all the individual rate orders. So for example, for this reaction, the rate is to the first order of N2O5. Since it's the only thing that's determining the rate, the overall order is a first order. For this reaction, you've got two reactants. Each of them has a first order, so the rate is actually second order overall. Here you have another reaction where it's dependent on NO squared, so there's a second order, and just H2 first order. So a 2 plus 1 is third order overall. So even though for any one particular component we usually only see a 0, 1, or 2 order, you can have an overall order be much higher than a second order. All right, how can we find out the rate order of a reaction? Well, in this case, you're going to need to use data. So we're going to perform experiments as we change concentrations of things. We're going to measure how much the rate changes. So this is how you're going to do it if you're given rate data. So you already know what the rate of the reaction is. And I can use the information this way. So I've got 2A plus B yields R plus S. So how am I going to deal with that information? Well, for A, what I'm going to do is I'm going to hold B constant. So if I look at experiments 1 and 2, B is constant, so B is not changing. So the only thing that's influencing the rate of the reaction is what the concentration of A does. So for 1 and 2, I can see that as I double the concentration, the rate goes up by a factor of 4. So this is a perfect example of a second order for substance A. It is simply a coincidence that there is a coefficient 2 there. It doesn't have to be second order just because there's a 2 there. This 2 has nothing to do with this 2. How about for B? Now what we want to do is we want to hold A constant. So we're going to compare experiment 2 and 3, where A is constant, but B is doubling. When B doubles, what happens to your rate? Nothing. So in this case, the rate order for B is actually a 0 rate order. So overall, what's my rate order? Second order for this, 0 order for this. Overall, the rate is second order. So this is how I would write the rate law. And overall, since B to the 0 is irrelevant, it's 1, we wind up with a rate law that is just concentration of A squared times the constant. Okay, you can also do it mathematically. Sometimes this works for people, sometimes it doesn't. Me personally, I think the logic just helps. But what you can do is you can set up a ratio, essentially. So the rates of the two divided by the rate expressions of the two, you can cancel out everything. You get all of this, and personally, I think this is more confusing. But you cancel out the constants, and what you wind up with is what the rate order for A is going to be. You've got 1 to the n divided by 0.5 to the n. Well, and that's equal to 4, so 4 equals 2 to the n. So what's n? 2, second order. So you can figure it out this way. Like I said, I think it's just easier to look at it logically. All right, if we take a look at the rate law in a different way, we got to look at integrated rate laws. So this is where you have, rather than knowing what the actual rate of the reaction is, this is if you just have time. So how long did it take? Not what the rate is, not change in concentration per time, but how long the reaction took. Okay, so integrated rate laws can be used to determine a few different things. You can use it to figure out the concentration of the reactant remaining at any time from time 0. You can use it to figure out the time required for a given fraction of a sample to react. You can use it to figure out the time required for the reaction concentration to fall to a certain level. So you can use integrated rate laws in a bunch of different ways. But again, it's when you have time data, not rate data, that you're using this. So the last example was with rate data. This is with time data. Okay, so for integrated rate laws, if you have a 0 order, here's where all your calculus comes into play. So hopefully you have a little experience with it up to this point. We've got the derivative, we've got the integral, but basically the bottom line is giving us, in a 0 order reaction, and we're not going to worry about derivations of this, honest to goodness, because it doesn't matter. In a 0 order reaction, we wind up with, we can rearrange the equation into y equals mx plus b, where this is the concentration of the substance at whatever time. This is the concentration of the substance at the start. this is the time that has passed, and this is your rate constant. So if we do all our calculus to this idea, this is the reaction, this is the equation you wind up with. Okay, first order, you wind up with, notice the difference, not just the concentration of A, the natural log of A is equal to negative KT plus the natural log of A naught. Okay, so natural log of the concentration versus, if we go back, just the concentration. So this is what's going to become important. How do we express the concentration? So this is a linear relationship. Taking the concentration of the substances versus time gives you a linear relationship. For first order, you get a linear relationship when you take the natural log of the concentrations versus time. And for second order, you wind up with 1 over the concentration, giving you a linear relationship. So this is really the important part. So if you have a zero order reaction, if we graph all three of those expressions, and this is where using your calculator is going to come into play. What you want to do is, if you have all this time versus concentration data, you want to take and make a graph. Time obviously is going to be the same, but the y-axis is going to change. You've got, for zero order, you're going to do concentration of A. If it's first order, you're going to see the natural log of the concentration of A. If it's second order, you're going to see 1 over the concentration of A versus time. So when you graph all three of these, the linear relationship here winds up being the A, so you know it's a zero order. Here, same expression, but if it's a first order, you're going to have the linear relationship in the natural log. And if it's a second order, the linear relationship is going to be at 1 over A. Now notice that in some cases, the linear relationship is a negative slope. That's okay, as long as it's the linear relationship. So you can see the other two, not really close to being linear. The other two, not so linear. The very linear one is what's going to tell you what kind of relationship you have, what kind of order for that component you have. So to summarize these very important relationships, to get a linear relationship, you want to take the concentration of A versus time for zero order, the natural log of A versus time for first order, and 1 over the concentration of A versus time for second order. So these are the ones that are going to give you the linear relationship. So with that data that you collect, so you'll have time data and you'll have concentration data. When you graph those, in three graphs with these axes, you are going to see that this will help you determine what order reaction it is, because you're going to pick the one that's most linear. Okay, so for example, we've got time data, we've got concentration data. We want to know if the reaction's first or second order. It's got to be one of those two, because as the concentration changes, the time actually does change. So we're going to plot all of that information. We've got time. We've got just the straight up concentration. So if this were a linear relationship, it would be zero order. If this is a linear relationship, if we take the natural log of these concentrations, if this is a linear relationship, it's going to be first order. And if we take 1 over the concentration, this versus this is a linear relationship, will tell us that it is second order. So in your calculators, what you're going to do is make a little table first in order to calculate all this information. And then it's just a matter of letting the calculator then make those graphs for you. So when you do it, what do you see? Well, here is the natural log, not very linear. Here is 1 over the concentration, very linear. So we can conclude that this reaction is second order for the disappearance of NO2. K winds up being 0.543 because that is the slope of the line. All right, so we are going to pause to learn how to do it with the calculator, although I want